Welcome to the deep dive. Today, we're plunging into, well, what can sometimes feel like the murky waters of statistics and research design.
Yeah, it can seem a bit daunting.
It really can. But if that sounds like heavy lifting, definitely stick with us because whether you're aiming to conduct studies yourself or just, make sense of the latest findings, getting these fundamentals down is just absolutely key.
Totally agree. And for anyone tackling the EPPP, think of this as getting the essential toolkit for understanding that research landscape you'll encounter.
Right.
Our mission today is pretty straightforward. Take the materials you've shared and pull out the most crucial, digestible insights, the real core stuff explained in a way that hopefully sticks.
Okay, let's unpack this. Maybe start with the big picture, the main ways we even approach research.
Good starting point.
Right.
So broadly, we split research into two main camps, quantitative and qualitative.
Okay.
Quantitative usually starts with a theory, right? And then you use numbers, statistical analysis to see if your predictions actually hold up. It's all about measuring things precisely empirically.
So predicting things, seeing if one thing causes another, that's quantitative.
That's the heart of it, yeah. And within quantitative, you've got a couple of key styles. Experimental research is one. That's where we actively change something, a variable, to see its effect while trying really hard to control everything else.
Like a classic science experiment.
Exactly. It's our strongest tool for figuring out cause and effect.
Got it. And the other main quantitative type.
That'd be non-experimental or descriptive research. Here, we're more observing and describing what's going on or what's already happened.
So less hands-on manipulation.
Right. We might look at how things relate, like in correlational studies, or maybe analyze existing records, archival research, or just ask people questions with surveys. The key is we're not directly fiddling with the variables.
Okay, so if we see, say, a link between two things in a non-experimental study, we can't just jump to A causes B.
Precisely. Only those controlled experiments really let us strongly infer causality.
Makes sense. Now, qualitative research. That sounds like a different beast altogether.
It really is.
Yeah.
Qualitative is much more about exploring, understanding experiences, perspectives, the how and why behind things.
So less about the number.
Definitely.
Yeah.
Instead of starting with a big theory, it often builds understanding from, detailed observations, stories, interpretations.
Kind of a ground-up approach then.
Exactly. The focus is on rich, descriptive data. Think deep interviews trying to grasp someone's lived experience, or ethnographic studies where you immerse yourself in a culture.
Or analyzing narratives, maybe?
Yes, or focus groups, case studies. Lots of methods. They give you that deep, nuanced understanding.
So very broadly speaking, numbers versus narratives.
Yeah, that's a decent shorthand. Both super valuable, of course. But as our source material points out, for the EPPP especially, you really need a solid handle on those quantitative methods.
Right.
And a really foundational concept within quantitative work is this difference between populations and samples.
Okay, population versus sample. Let's break that down. What's the difference and why does it matter so much?
Okay, so the population is the entire group you're actually interested in studying.
Yeah.
Could be all teenagers, or all clinical psychologists, or, like in one of our examples, all children diagnosed with ADHD.
The whole shebang.
The whole shebang. But obviously studying everyone in that group is usually impossible, right?
Yeah.
Just not feasible.
Right, tracking down every kid with ADHD globally.
Nope. Exactly. So instead, we take a smaller group, a subset from that population. And that subset is our sample. Think of it like taking a representative slice of the whole pie.
And the goal is to learn from that slice.
Yes.
Yeah.
We study that sample, maybe kids with ADHD in a specific clinic who are trying a new cognitive intervention, and then we hope to take what we learn from them and apply it or generalize it back to the larger population of all kids with ADHD. That's generalizability.
Generalizability, making sure our findings from the small group actually mean something for the big group. How do we boost that? How do we make it more likely?
Well, the gold standard method is random sampling. That means every single person in the population has an equal chance of being picked for our sample.
Okay, equal odds.
That helps make our sample more likely to actually look like the population. Also, bigger samples generally help in making sure the sample is diverse.
But it's not a guarantee, right? Even with random sampling.
That's a really key point. It's not a guarantee, especially if your target population is quite specific or small to begin with.
Like, give me an example.
Okay, say you do a great job randomly sampling adults diagnosed with a really rare form of schizophrenia. Your findings might generalize well to other adults with that same specific diagnosis, but you couldn't just assume those results apply to all adults everywhere. The more niche the group, the more careful you got to be about generalizing too broadly.
That's a critical distinction. Okay, so let's talk more about how we actually get that sample in quantitative research, those different techniques.
Right. So first up is simple random sampling. Like we said, everyone has an equal chance. And importantly, selecting one person doesn't affect the chances of anyone else being selected.
Like drawing names from a hat.
Exactly. And technically, for true independence between draws, you need to put the name back in each time or use sampling with replacement.
Okay, makes sense. What's next?
Then there's stratified random sampling. This is where you first divide your population into meaningful subgroups, or strata. These could be based on age, ethnicity, income level, whatever's relevant.
So you carve up the population first.
Yep. And then you take a simple random sample from within each of those subgroups.
Ah, okay. Why do that?
It ensures that these important subgroups are represented in your final sample, usually in proportion to how common they are in the overall population.
So if we're studying, say, student success, and our school is 25% freshmen, 25% sophomores, etc., stratified sampling helps make sure our study sample has that same 25, 25, 25, 25 split.
Precisely. You'd randomly pick a certain number from each grade level. It guarantees representation.
Got it. And there was another one, cluster sampling.
Right, cluster sampling. Here, you randomly select naturally occurring groups, or clusters, of people first. Then, you either study everyone within those selected clusters, or you take a random sample of individuals from within those selected clusters.
Why would you use that?
It's really useful when the population is spread out geographically, or maybe you don't even have a full list of every individual.
Oh.
The source is a good example. Studying individuals with autism.
Okay.
Instead of trying to list every person, you might list clinics specializing in autism, randomly pick a few clinics, those are your clusters, and then study the individuals who attend those specific clinics.
So picking groups instead of individuals initially. Okay. And now, this next point seemed really important in the source material. The difference between random sampling and random assignment. People get these mixed up, don't they?
Oh, constantly. And it's absolutely crucial to understand the difference. It's fundamental to research design. So, let's be clear. Random sampling is all about how you get participants into your study from the population.
How you select them initially.
Yes. The main goal is getting a representative sample so you can generalize your findings. Think. Selection from the population.
Got it. Selection.
Random assignment, on the other hand, happens after you've already got your participants. It's about how you put those participants into the different groups or conditions within your study, like the treatment group versus the control group.
So once they're in the study, where do they go?
Exactly. The main goal of random assignment is to make the groups as similar as possible before the study starts. So if you see differences later on, you can be more confident it was your intervention, your independent variable, that caused them, not some pre-existing difference.
Ah, okay.
This is absolutely key for internal validity, for making those cause and effect claims in experiments. Think, grouping within the study.
Okay, that's super clear. Sampling gets them in the door for generalizability. Assignment puts them in rooms for internal validity and causality.
Perfect.
Let's talk more about validity then. What does it actually mean for a study to be valid?
Validity, in research terms, is basically about the accuracy and trustworthiness of your findings and conclusions. Are they sound? Are they meaningful?
Makes sense.
And we usually talk about two main kinds: internal validity and external validity. Let's start with internal.
Okay.
Internal validity is about how confident you can be that your treatment or intervention, your independent variable, is the actual cause of the outcome you observed in your dependent variable.
So it's about ruling out other explanations, making sure it was really our thing that did it.
Exactly. Was it the therapy or was it something else entirely? High internal validity means you have strong evidence pointing to your therapy.
How do we get that? How do we boost internal validity?
Mostly through really strong, rigorous research methods.
Mm-hmm.
Using control groups, random assignment like we just discussed, minimizing errors and biases in how you run the study.
And controlling for those other explanations.
Yes, controlling for extraneous or confounding variables. Those are the alternative explanations, the something else that could have caused the outcome.
Confounding variables, the party crashers of research. What are some common ones we need to watch out for? Those threats to internal validity.
Yeah, there are several classic threats. One is attrition, when people drop out of your study.
Right.
If the people who drop out are different in some important way from those who stay, it can mess up your results. It might look like your treatment worked, but maybe it was just that the less motivated people left, for instance.
Okay, so dropout bias. What else?
History effects. These are external events that happen during your study that could influence participants. Imagine a big economic downturn happens while you're studying a job training program's effect on employment. That external event could affect your results.
Right. Something outside the study impacts the participants.
Exactly. Then there's maturation. This refers to changes within the participants themselves over time that are just natural. Kids get older, people learn things naturally, maybe they just get bored or tired over a long study. These internal changes could be mistaken for a treatment effect.
So history is external events. Maturation is internal changes in people over time.
Precisely. Another threat is instrumentation. This is about changes in how things are measured during the study.
How so?
Maybe the test itself gets revised halfway through, or the people doing the ratings get better or worse at it over time. Any change in the measurement tool or process can create apparent differences that aren't due to the treatment.
So the ruler changes, not necessarily the thing being measured.
You got it. Then there are testing effects. Just taking a test once can affect how people score if you give it to them again later.
Like Mactus effects.
Yeah, or they might remember answers, or just get less nervous the second time. It's the act of being tested itself that causes a change. Sometimes using a post-test only design helps avoid this.
Okay.
Statistical regression, or regression to the mean, is another one. It's a bit tricky. Basically, if you pick people for your study because they have extreme scores really high or really low, their scores are likely to be closer to the average the next time you measure them, just due to random statistical fluctuation.
So extremes tend to naturally move back towards the middle.
Exactly. And if you're not aware of it, you might think your intervention caused that shift when it was just statistics doing its thing.
Interesting. What about the groups themselves?
Selection bias is a huge one. This happens if your groups are different in some important way right from the start before you even do anything.
Like if the treatment group was already more motivated than the control group?
Perfect example. And random assignment is our best defense against that.
Right.
And finally, you can have interactions with selection. This is where you have that initial group difference, and one group is also more vulnerable to another threat, like a history effect. It's like a double whammy.
Wow, okay. Lots to keep track of to make sure our study is internally sound. Now let's flip the coin. External validity. What's that about?
External validity, like we touched on with sampling, is all about generalizability.
Yeah.
To what extent can you take the findings from your specific study and apply them confidently to other people, other settings, other times, maybe slightly different versions of the treatment?
So how well does it translate to the real world, basically?
That's a good way to put it. It's about the broader applicability.
And what things can threaten that? What limits our ability to generalize?
The source mentions a few key ones. Interactions between testing and treatment. Maybe your treatment only works if people get a pre-test first, which doesn't always happen in the real world.
Okay.
Interactions between selection and treatment. Maybe your treatment only works for the very specific type of people who volunteered for your study and wouldn't work for others.
Makes sense.
Reactivity, sometimes called the Hawthorne effect. People might act differently just because they know they're in a study and being watched.
Right. Being observed changes behavior.
Yep. And multiple treatment interference. If participants are getting other treatments or interventions at the same time, it's hard to know if your specific treatment would work the same way on its own. All these things can make it tricky to say how well the results apply elsewhere.
Okay, so internal validity is about whether the effect is real within the study. External validity is about whether it applies outside the study. Got it. Now, let's get back to basics. The things we're actually measuring and manipulating. Variables.
Right. The core components, we have independent variables, or IVs. These are the things the researcher thinks might be a cause or an influence. It's what defines the different groups participants are in, or a characteristic that differentiates them.
So it can be something we change or something that's just there.
Exactly. It could be something you manipulate, like trying different therapy types, EMDR versus CBT versus play therapy maybe. Or it could be a pre-existing characteristic, like age group or diagnostic category.
And the key is you need at least 2 levels, right, for comparison.
Absolutely crucial. You need at least 2 groups or conditions to compare. You can't see the effect of therapy A without comparing it to something else, maybe therapy B, or a no-therapy control group.
Okay, and the dependent variable, the DV, that's the outcome.
Yep. The dependent variable is what you measure to see if the independent variable had any effect. It's the outcome you're interested in, the thing you hope changes based on the IV.
So in that therapy example.
Right. If the therapies, EMDR, CBT, play therapy, are the levels of your IV, Then maybe scores on a trauma symptom checklist would be your DV. You're measuring those scores to see if they differ depending on which therapy someone received.
Perfect. And there was that handy trick for spotting them.
Yeah. Often study titles or descriptions sound like the effects of independent variable on dependent variable. So the effects of therapy type on trauma symptoms. It's a good clue.
Nice shortcut. Okay, so we have our IVs and DVs. How do we actually measure them? That gets us to scales of measurement, right?
Yeah.
NOIR.
Exactly. Nominal, ordinal, interval, ratio, NOIR. These scales tell us about the nature of our data and what we can do with it statistically.
Let's go through them. Nominal.
Nominal is the simplest. Just categories, labels, no inherent order. Think gender, ethnicity, a type of diagnosis, yes, no answers. You can count how many fall into each category, frequencies, but you can't average them or say one is higher than another.
Just buckets.
Just buckets. Next is ordinal. Here, the categories do have a meaningful order, a rank.
Love what?
Thinker scales strongly disagree, neutral, agree, strongly agree. You know the order, but you can't assume the distance between each step is equal.
Ah, the gaps might be different sizes.
Exactly. The difference between disagree and neutral might not feel the same as the difference between agree and strongly agree. So ranking is okay, but calculating a mathematical average, a mean, is usually not appropriate.
Got it. Ordered, but maybe uneven steps. What's after ordinal?
Interval scale.
Yeah.
Now we have order, and the intervals, the steps between the values are equal.
Okay, like temperature.
Temperature in Celsius or Fahrenheit is a classic example. Or IQ scores. The difference between 90 and 100 IQ points is the same amount as the difference between 100 and 110. You can calculate meaningful averages with interval data.
But there's a catch.
The catch is there's no true absolute 0 point. 0 degrees Celsius doesn't mean no temperature, and an IQ of 0 doesn't mean no intelligence whatsoever. 0 is just another point on the scale.
Okay, equal steps, but 0 isn't nothing. And the last one, ratio.
Ratio scale. This has everything. Order, equal intervals, and a true absolute 0.
Meaning 0 actually means the absence of the thing.
Exactly. Think weight, height, reaction time, number of cigarettes smoked, income in dollars. 0 weight means no weight. 0 cigarettes means no cigarettes. Because of that true 0, you can do the most complex math, including forming meaningful ratios, like saying someone weighs twice as much as someone else.
And knowing these scales is super important for picking the right STAPS test later, isn't it?
Absolutely critical. You have to know the scale of measurement for your variables to choose the right statistical analysis. Using a test designed for interval data on nominal data, for example, just gives you nonsense.
Okay, super important. So variables measured. Now, in experiments, we usually have an idea, a prediction about what we'll find. That's the hypothesis, right?
Precisely. A hypothesis is your testable prediction about the relationship between the IV and the DV. It's what you think will happen.
And in statistics, we test this against something called the null hypothesis.
Right. When we do a statistical test, we're essentially pitting two ideas against each other. The null hypothesis and the alternative hypothesis.
Okay, what's the null?
The null hypothesis, often written H-arrow, is the hypothesis of no effect or no difference. It states that, in the population, the IV has no impact on the DV. Any difference you see in your sample is just due to random chance or sampling error. It's the default assumption.
So nothing interesting is happening here.
Pretty much. The alternative hypothesis, H or HA, is the opposite. It states that there's a real effect or relationship in the population. The IV does influence the DV, and the difference you see in your sample likely reflects that real effect. This is usually what the researcher actually believes or hopes to find.
So null is no effect, alternative is there is an effect. And these are always statements about the population.
Always. Even though we only have sample data, the hypotheses are about the bigger picture, the population values.
And we use our sample data to make a guess about which hypothesis is more likely.
Exactly. We use inferential stats like t-tests or NOVAs to see how likely our sample results are if the null hypothesis were true.
Okay, let's use that impulsivity intervention example again. What would the hypotheses be?
Okay. The null hypothesis would be the cognitive intervention has no effect on impulsivity levels in the population of children with ADHD. The average impulsivity score is the same for treated and untreated kids.
No difference.
No difference. The alternative hypothesis would be the cognitive intervention does affect impulsivity levels in the population. We expect the average impulsivity scores to be different between the groups.
And our stats test gives us a probability, helping us decide.
Right. If the results we see in our sample are really unlikely to happen by chance alone, if the null were true, usually meaning a low p-value, We reject the null hypothesis
And favor the alternative.
and favor the alternative, concluding there likely is an effect. If our results aren't that unusual under the null, we fail to reject or retain the null hypothesis.
Okay, reject the null or fail to reject it. But we could be wrong, right? We're just making an inference based on probability.
Absolutely. We never know for sure if we made the right decision over the population. And that's where type I and type 2 errors come in, along with statistical power.
Right, okay. Let's tackle power first. What is statistical power?
Power is the probability that your study will correctly detect an effect if there actually is a real effect to be found in the population. It's the ability to correctly reject a false null hypothesis.
So the power to find something real.
Exactly. You want high power so you don't miss genuine effects.
What gives a study more power?
Three main things generally boost power. First, a larger sample size. More people, more power.
Makes sense.
Second, a larger effect size. If the treatment has a really strong impact in reality, it's easier to detect, so more power.
A bigger signal is easier to hear.
Perfect analogy. And third, the alpha level you set your threshold for statistical significance. A slightly higher alpha, say point interval instead of 0.05, makes it easier to reject the null, which increases power if the null is actually false. But that comes with a trade-off.
The trade-off being type I error.
Exactly. A type I error is a false positive. It's when you reject the null hypothesis when it's actually true. You conclude there is an effect, but you're wrong. The results were just due to chance.
The false alarm.
The false alarm. The probability of making a type I error is equal to your alpha level. So if alpha is 0.05, you have a 5% chance of making a type I error if the null is true.
Okay. And the other error, type 2.
A type 2 error is a false negative. It's when you fail to reject the null hypothesis when it's actually false. You conclude there's no effect, but you're wrong. There really was an effect in the population, you just missed it.
Missing something real.
Missing something real. This often happens when a study lacks power. Maybe the sample size was too small or the effect size was weak. The probability of a type 2 error is called beta. We can't set beta directly like alpha, but higher power means lower beta.
So type 1, seeing something that isn't there, alpha. Type 2, missing something that is there, beta. And power is the ability to correctly spot something real, 1 beta.
You've got it.
Right.
And we never know for certain which situation we're in for any given study. That's why interpreting results requires understanding these possibilities. The decision table in the source material is really good for visualizing that.
It's definitely good to review. Okay, we've mentioned describing data and making inferences. Let's formalize that. Descriptive versus inferential statistics.
Right. Descriptive statistics do just what the name says. They describe and summarize the basic features of the data you've collected from your sample.
Like averages and spread.
Exactly. Measures of central tendency, mean, median, mode tell you what's typical. Measures of variability, standard deviation, range, variance tell you how spread out the scores are. And things like correlation coefficients describe relationships between variables in your sample. It's all about painting a picture of the data you have.
Just the facts for our sample.
Just the facts. Inferential statistics, on the other hand, try to go beyond the sample. They use probability theory to make inferences or educated guesses about the larger population from which your sample was drawn.
This is where significance testing comes in.
Yes. Inferential stats help us decide if the patterns we see in our sample, like a difference between group means, are likely real patterns in the population, or if they could plausibly be just due to random chance, that sampling error we talked about. Generalizability and statistical significance are key concepts here.
Okay. Descriptive summarizes the sample. Inferential makes guesses about the population. Now, let's dive into some of those inferential tests used for looking at differences between groups. You mentioned parametric and nonparametric.
Yeah. It's a major fork in the road for choosing tests. Parametric tests are generally preferred when possible because they're more powerful but direct at detecting real effects.
But they have requirements.
They do. They rely on certain assumptions about your data. Primarily, that your dependent variable is measured on an interval or a ratio scale, that the data in the population follows a normal distribution, the bell curve, and that the variability, or variance, is roughly equal across the groups you're comparing, homoscedasticity.
Okay. Normal distribution, equal variance, interratio data. What if we don't meet those, or have nominal ordinal data?
Then you turn to nonparametric tests. These make fewer assumptions about the data distribution. They're the go-to for nominal or ordinal data, or when your interval ratio data badly violates the parametric assumptions. Things like chi-square tests, which we'll discuss, Mann-Whitty test, Wilcoxon signed rank test. There are quite a few. They're more flexible. But the trade-off is they generally have less statistical power than their parametric counterparts if the parametric assumptions are met.
Okay. Our source focused on three main inferential tests: chi-square, t-tests, and ANOVA. Let's start with chi-square. What's it used for?
Chi-square tests are designed specifically for analyzing categorical data, the nominal data, the buckets. They basically compare the frequencies you observed in your sample categories to the frequencies you would expect based on some hypothesis, often the null hypothesis of no relationship or no difference from a known distribution.
Observed versus expected counts.
Exactly. There are two main types highlighted. The single-sample chi-square, sometimes called a goodness of fit test.
What's that test?
It's used when you have one categorical variable, and you want to see if the proportions or frequencies across its categories in your sample match some known or hypothesized proportions in the population. Like, does the ethnic breakdown of clients at your clinic match the census data for your area?
Comparing one sample's category counts to a known pattern,
Okay.
and the other chi-square.
The multiple sample chi-square, usually called the chi-square test of independence, this is used when you have two or more categorical variables, and you want to see if there's a relationship and association between them.
Like, are two categorical things linked?
Right. The example given was, is there a relationship between a psychologist type of degree, PhD versus highest ID category 1, and their main theoretical orientation, CBT versus psychodynamic versus humanistic category 2? It tests if the choice of orientation is independent of the degree type.
Okay, chi-square for categorical counts and relationships. Next up, t-tests. What's their job?
T-tests are workhorses for comparing the means of two groups. Keyword, two. They fall under parametric tests, so ideally your dependent variable is interval or ratio, and you meet those assumptions about normality and equal variances, roughly.
And there are different kinds of t-tests.
Three main ones, depending on how your two groups are related. First, the t-test for a single sample.
When do you use that?
When you have one group's mean score, and you want to compare it to a known population mean. Like, did the students in my class who got a special tutoring program score significantly different on a standardized test compared to the known national average score for that test?
Your sample mean versus a known population mean. Got it.
Second, the independent samples t-test. This is probably the most common one. It compares the means of two separate independent groups.
The classic treatment versus control group.
Exactly. Does the group that got therapy A have different average depression scores than the group that got therapy B, or placebo? The groups contain different people, unrelated to each other.
Okay. Two separate groups. And the third t-test.
The dependent samples t-test, also called paired samples or related samples t-test. This is used when your two sets of scores are related or linked in some way.
How so?
Two main scenarios. Either you measure the same group of people twice, typically before and after an intervention, pre-test, post-test design, or you have two groups, but they're intentionally matched in pairs based on some relevant characteristic, like matching people on initial symptom severity, and then one member of each pair goes into each group.
So same people twice, or different people matched up. Okay. T-tests for comparing two means. But what if we have more than two groups we want to compare?
Then you move up to analysis of variance, or ANOVA.
ANOVA. Sounds important.
It is. ANOVA lets you compare the means of two or more groups simultaneously. Like t-tests, it's parametric, so same assumptions apply ideally. Interval ratio DV, normality, equal variances.
Why not just do a bunch of t-tests, like compare group A to B, then A to C, then B to C?
You could, but it's generally a bad idea. Every time you run a t-test, there's that alpha chance of a type I error. If you run lots of tests on the same data, your overall chance of making at least one type I error inflates dramatically. It's called the experiment-wise error rate. ANOVA cleverly avoids this by testing for any difference among all the group means in one go.
It controls that error inflation. Smart. What kinds of ANOVA are there? The source mentioned one way.
Yep. A one-way ANOVA is the simplest. You use it when you have one independent variable with two or more levels, your groups, and one dependent variable.
Example.
Comparing the effectiveness of three different teaching methods, 5V with 3 levels, on student test scores, the DV. The one-way ANOVA tells you if there's any significant difference somewhere among those three group means.
Okay. One IB, multiple groups, one DV. What if we have more than one IV?
Then you use a factorial ANOVA. This is for situations with two or more independent variables being looked at simultaneously, still with one dependent variable.
What's the advantage of that?
It's really powerful because it lets you look at two things: main effects and interaction effects.
Okay, break those down. Main effect.
A main effect is the overall effect of one independent variable on the dependent variable, ignoring the other independent variables for a moment. You'd have a main effect for each IV in your study.
So the effect of IVA on its own and the effect of IVB on its own?
Right. But the really interesting part is often the interaction effect.
That sounds like when the IVs work together or against each other.
Exactly. An interaction effect means the effect of one independent variable depends on the level of the other independent variable. The effect isn't straightforward. It changes based on the combination.
Can you give that ADHD treatment example again?
Sure. Let's say IVA is treatment type, behavioral versus meds, and IVB is ADHD subtype, inattentive versus hyperactive. A main effect might show meds work better overall, but an interaction might show that meds work great for the hyperactive subtype, but behavioral therapy actually works better for the inattentive subtype. The effect of treatment depends on the subtype.
That's way more nuanced than just looking at one thing at a time. Very cool. The source also quickly mentioned Anankova and Manova.
Yeah, just briefly, Anankova stands for analysis of covariance. It's basically an ANOVA, but it lets you statistically remove the influence of an unwanted variable, a covariate that might be clouding the picture. Like if your treatment and control groups accidentally differed slightly in age at the start, Anankova can adjust for that age difference.
So eating up the comparison.
Kind of, yeah.
Hmm.
And Mananova is multivariate analysis of variance. That's what you use when you have one or more IVs, but multiple dependent variables, all interval ratio, that you want to analyze together because they might be related.
Like looking at effects on both anxiety and depression scores simultaneously.
Exactly. It considers the whole set of outcomes.
Okay, powerful tools for complex questions.
Okay.
Now shifting slightly. The source talked about multivariate techniques specifically for prediction. How's that different?
The focus shifts. Instead of primarily looking for group differences caused by an IV, these techniques are more about identifying which variables, predictors, best forecast an outcome, criterion, often used in correlational or non-experimental designs.
So using variable X and Y to predict variable Z.
Pretty much. Multiple regression analysis is a key one. You
Yeah.
use it when you have two or more predictor variables trying to predict a single criterion variable that's interval or ratio.
Like using undergrad GPA and GRE scores, predictors, to predict success in grad school. Criterion may be measured by first-year GPA.
Perfect example. Multiple regression tells you how well that set of predictors works overall, using R and R squared, and sometimes the unique contribution of each predictor.
Okay. What else was mentioned for prediction?
Canonical correlation came up. That's more complex. It's for when you have multiple predictors and multiple criteria, all interval ratio. It looks for relationships between the set of predictors and the set of criteria.
And what if the thing we're trying to predict is a category, not a score? Like predicting dropout versus graduate.
Then you'd use discriminant function analysis. It uses two or more predictors, usually interval ratio, to predict which group someone belongs to on a nominal criterion variable. The grad school completion example is spot on for this.
Predicting group membership.
Right. And logistic regression is very similar. Also predicts a nominal outcome, but it has fewer statistical assumptions than discriminant analysis. So it's often used when those assumptions aren't met.
Okay, different prediction tools for different types of outcomes.
Oh.
Now, the last big chunk of the source material was on program evaluation strategies, applying these research ideas to real-world programs.
Exactly. Program evaluation uses research methods to assess how well programs are designed, implemented, and achieving their goals. It's super practical.
Where does it start?
It really should start with a needs assessment. That's systematically figuring out the problem the program is supposed to solve. What are the gaps between how things are and how we want them to be? You gather data, identify needs, prioritize, and that informs the program design.
Makes sense. Know the problem before you try to fix it.
Definitely. Then early on, you might do a cost-benefit analysis weighing the program's costs against its expected outcomes. Is it worth it?
Okay. What about once the program is running?
During implementation, you do process evaluation or implementation evaluation. This checks. Is the program actually being delivered the way it was planned? Are the activities happening as intended?
Keeping things on track.
Yep. Formative evaluation happens during the program's development or operation with the goal of improving it along the way, gathering feedback, making adjustments.
And then at the end?
At the end, you have summative evaluation. This assesses the overall results, the impact. Did the program work? Should it be continued, expanded, stopped? Outcome evaluation is closely related, focusing specifically on whether the program achieved its intended goals and produced the desired changes in participants.
So a whole cycle of evaluation from needs to outcomes. And the very last point was about community involvement and getting research findings out there. Dissemination.
Yes, and it's crucial. Research shouldn't just live in journals. Dissemination is about actively sharing findings with stakeholders, the people who can actually use the information. Policymakers, practitioners, community members, the participants themselves.
And it's not just a one-way street, right?
No, the source stressed it should be a dialogue, engaging with the community, listening to their perspectives.
Why is that so important?
Well, effective dissemination increases awareness, builds trust, makes it more likely that evidence-based practices actually get adopted. Plus, getting local input helps make interventions more relevant, culturally appropriate, and ultimately more impactful. It connects research back to the real world it aims to serve.
Fantastic. Okay, so to try and wrap this all up, quite a journey today. We went from broad research approaches, quantitative and qualitative.
Dove into populations, samples, and how to get them representatively.
Talked a lot about validity, making sure our study is internally sound and externally generalizable, and all those tricky threats.
Defined our core building blocks, independent and dependent variables, and those NOIR scales of measurement.
Unpacked hypotheses, null versus alternative, and the risks of type I and type 2 errors, plus the importance of power.
Distinguished descriptive stats from inferential stats.
And then walked through key tests, chi-square for categories, t-test for comparing two means, ANOVA for comparing more than two, plus those multivariate techniques for prediction.
Right, and finished up with program evaluation strategies and the vital role of community dissemination.
It really covers the foundational landscape from the source material.
It does. Hopefully breaking it down like this makes these concepts feel a bit less intimidating and more, practically useful.
Absolutely. And hopefully for you listening, it gets you thinking about how these ideas connect to your own work or studies you read.
So maybe a final thought to leave you with. Now that you've got this deeper dive into stats and research design principles, how does this empower you? How might you be a more critical consumer, or maybe even a more thoughtful producer, of knowledge in your own field?